A monster is feeding in the shadows of space, and it's far hungrier than we ever imagined. NASA's James Webb Space Telescope just caught it in the act, devouring matter at a terrifying rate. This is the supermassive black hole at the heart of the Circinus Galaxy, and what we've discovered changes everything we thought we knew about these cosmic predators. Stay with me, because by the end of this video, you'll understand one of the most violent and fascinating processes happening in our universe right now. What just happened? In January 2026, NASA announced something extraordinary. The James Webb Space Telescope, humanity's most powerful eye in space, turned its gaze toward a relatively nearby galaxy called Circinus. What it found there shocked astronomers around the world. The supermassive black hole lurking at the center of this galaxy isn't just active, it's absolutely ravenous, consuming material at rates far beyond what our previous observations had suggested. We're talking about a cosmic feeding frenzy happening on a scale that's almost impossible to comprehend. But here's what makes this discovery truly groundbreaking. JWST didn't just see that the black hole was feeding, it revealed the intricate machinery that makes this feeding possible. Massive structures of dust and gas called torus formations that act like cosmic funnels, channeling matter directly into the black hole's gravitational grip. To put this in perspective, this black hole has a mass of several million times our sun. Imagine something so dense and powerful that it warps the very fabric of space and time around it. And now we know it's consuming the equivalent of several Earth masses every single day. That's not a typo. Every single day. Meet the Circinus Galaxy. Before we dive into what's happening at its heart, let's talk about the Circinus Galaxy itself, because this cosmic neighbor has been hiding in plain sight for decades. Located approximately 13 million light-years away from Earth, Circinus is actually one of the closest active galaxies to us. Now, 13 million light-years might sound incredibly distant, and it is. The light we're seeing from Circinus today left that galaxy when our earliest human ancestors were still millions of years away from walking the Earth. But in cosmic terms, this is practically our backyard. So why haven't you heard more about Circinus before? Here's the fascinating part. The galaxy lies in what astronomers call the zone of avoidance. This isn't some sci-fi force field. It's simply the region of sky where our own Milky Way galaxy's dense disk blocks our view. Imagine trying to see something on the other side of a thick wall of dust and stars. That's the challenge Circinus has presented to astronomers for years. Circinus is classified as a Seyfert galaxy, which is a special type of galaxy with an extremely bright, active nucleus. Seyfert galaxies are fascinating because they're essentially on in a way most galaxies aren't. While our Milky Way's central black hole is relatively quiet, taking occasional small snacks, Seyfert galaxies like Circinus have black holes that are constantly feeding, constantly active, constantly putting out enormous amounts of energy. The galaxy itself is a spiral, somewhat like our own Milky Way, with beautiful arms of stars, gas, and dust spiraling outward from its center. But it's what's at that center that makes Circinus truly special. The torus structure explained. Now we get to the heart of the matter. Literally, at the very center of the Circinus Galaxy sits a supermassive black hole, and surrounding it is one of the most elegant and efficient feeding mechanisms in the universe, the torus. Picture a donut. Not a small donut, imagine a donut that's several light years across. That's the scale we're talking about here. This torus is made up of incredibly dense clouds of dust and gas, all rotating around the black hole in a thick, ring-shaped structure. The material in this torus is so dense that visible light can't penetrate it, which is exactly why previous telescopes like Hubble struggled to see what was really happening here. But JWST changes everything. JWST observes in infrared wavelengths, essentially heat radiation. Infrared infrared light can penetrate through dust clouds that would completely block visible light. It's like having X-ray vision for cosmic dust. When JWST looked at Circinus, it could see right through that torus and observe the feeding mechanism in unprecedented detail. So how does this cosmic donut actually feed the black hole? Think of it like a whirlpool drain, but on a galactic scale. The torus isn't static, it's constantly churning, with material gradually spiraling inward. As gas and dust from the torus get closer to the black hole, gravity intensifies. The material starts moving faster and faster, forming what's called an accretion disk. This accretion disk is where things get really violent. Matter in the accretion disk is moving at significant fractions of the speed of light. We're talking about thousands of kilometers per second. At these speeds, friction becomes extreme. The material heats up to millions of degrees, becoming so hot that it glows brilliantly across the electromagnetic spectrum. What JWST revealed is that the torus structure around Circinus's black hole is far more massive and far more active than we previously understood. There's simply more material available to feed the black hole, and the feeding mechanism is more efficient than our models predicted. The torus isn't just passively sitting there, it's an active, dynamic structure constantly channeling matter inward. How hungry is this black hole? Let's talk numbers, because the scale of this cosmic feast is genuinely mind-blowing. Previous estimates, based on observations from older telescopes, suggested that the Circinus black hole was consuming matter at a certain rate. Let's call it the expected rate for an active galaxy nucleus of its size. But JWST's new observations have rewritten those estimates. The actual consumption rate is significantly higher, potentially several times what we thought. But what does consuming material actually mean? Here's what's happening. As matter spirals closer and closer to the black hole, it eventually crosses a point of no return called the event horizon. Once anything, matter, light, information crosses the event horizon, it's gone. It becomes part of the black hole itself, adding to its mass. Before it crosses that threshold, though, the material in the accretion disk releases enormous amounts of energy. The black hole at the center of Circinus is releasing energy equivalent to billions of stars like our sun. Think about that. Billions of stars worth of energy, all coming from a region of space smaller than our solar system. If you could somehow watch this process up close, from a very, very safe distance, you'd see a maelstrom of superheated gas swirling at incredible speeds, glowing so brightly it would outshine every star in the galaxy combined. You'd see jets of material being expelled at nearly the speed of light, shot out perpendicular to the accretion disk by powerful magnetic fields. You'd witness the most extreme environment in the universe, the edge of a black hole's feeding zone. To give you a sense of scale, if Earth were the size of a grain of sand, this black hole would still be consuming the equivalent of entire beaches worth of material every single day. The amount of mass being converted to energy is staggering. Einstein's famous equation, E equals mc squared, shows us that even small amounts of mass can produce enormous energy, and we're talking about the mass of multiple planets being processed continuously. Why this matters. You might be thinking, okay, there's a hungry black hole 13 million light years away. Why should I care? Great question, and the answer reveals something profound about how our universe works. Supermassive black holes aren't just cosmic vacuum cleaners sitting passively at the centers of galaxies. They're actually the master sculptors of those galaxies. There's a deep, fundamental connection between a galaxy and its central black hole. They grow together, they evolve together, and they shape each other in ways we're only beginning to understand. When a black hole feeds as actively as the one in Circinus, it doesn't just consume matter quietly. The energy released during this feeding process creates powerful outflows and jets that blow gas and dust throughout the entire galaxy. This process, called feedback, can actually regulate star formation across the entire galaxy. Here's how it works. Stars form from clouds of cold gas and dust. When the central black hole is actively feeding and releasing enormous amounts of energy, that energy can heat up gas clouds throughout the galaxy, or even blow them out of the galaxy entirely. This means fewer stars can form. It's like the black hole is saying, "Slow down, galaxy, don't make stars too fast." This might sound destructive, but it's actually crucial. Without this feedback mechanism, galaxies would convert all their gas into stars too quickly, burning out in a cosmic blink. The black hole's feeding helps pace the process, allowing galaxies like Circinus to sustain star formation over billions of years. The Circinus discovery also helps us understand distant quasars, those incredibly bright objects we see from the early universe. Quasars are essentially supermassive black holes in their most active feeding phase, similar to what we're seeing in Circinus, but even more extreme. By studying Circinus up close, we learn how those distant cosmic lighthouses work. And here's a humbling thought. Our own Milky Way galaxy has a supermassive black hole at its center called Sagittarius A. Right now, it's relatively quiet,